I would like to start thanking the organizers for inviting me to participate in this workshop. And my talk I will show you how we use AFM to get information about the structure and the functionality of organic semiconductors in relation with the performance in devices. I will focus on small conjugated molecules, as those here, since, as you know, and in contrast with polymers, they form crystalline structures. And in thin films, and for the application in devices, these organic assemblies, they form structural and morphological features at a broad range of length scales. For example, this is very well illustrated in this scheme. In the top panel, corresponding to the so-called bulk heterojunction solar cells, and in the bottom panel, in the application of organic semiconductors for organic field effect transistors. In my talk, I will focus on organic field effect transistors because this is a common testing device to learn and to study the basic electrical properties of organic field effect transistors and to correlate these properties with structural information. So in an organic field effect transistor, so it's important at the molecular scale, the packing of the molecules, also the presence of boundaries and grain boundaries, about the size and the crystalline quality of those domains and those grains, and also the orientation of them on the surface. And since many years, it has been also recognized the importance of the interfaces. Since on the bottom dielectric interface, the dielectric interface in this bottom gate field effect transistors, this is at this interface where the transport channel is formed. The orientation and the crystalline quality of the organic molecules of this interface is critical. And one common strategy has been used since many years to use self-assembled monolayers to modify these properties, to control the threshold voltage of the organic field effect transistors, and even to dope this transport channel. This we show in this publication. The other critical interface is the electrode, because this determines the injection properties in the device. And also a very common strategy has been used, the use of self-assembled monolayers with a permanent electrical dipole to tune and to adjust the work function to have an ohmic injection in the device, or more recently to use of molecular dopants inserted here between the electrode and the organic layer. So one of the challenges still in this field is to control how the molecules arrange at different length scales in the device and also at the interfaces to optimize electrical properties in the device. So in my talk, I will show you how we combine the complementary information that we get from Kelvin-proof force microscopy to learn about the electronic properties of the interfaces, work function, electrical dipoles, charge transfer, contact resistance, etc., and how we use frictional force microscopy as a tool for structural characterization. Since Tobias was already talking and giving nice examples about the use of Kelvin-proof force microscopy, and I think it will be more talks focusing on this technique. I will mostly give an introduction about frictional force microscopy and in particular about what is called transverse shear microscopy. And I will give you two scientific examples from our group. How we use AFM in the vertical phase separation on a blend of organic field effect transistors, and a little bit about surface molecular doping. Now, so probably you know that frictional force microscopy was one of the earliest development of AFM. So measured in contact mode, it measures the torsion of the cantilever caused by the lateral force while sliding on the surface. So this force is reversed in the backward direction, and the area enclosed in this loop is called frictional loop and is related with the dissipated energy. This was a very important development because it allowed for the first time to explore friction at the atomic scale. And at the atomic scale, the lateral force is showing this kind of tooth shape, which is due to the stick-slip mechanism due to the interaction of the tip with the periodic atomic potential in the surface. So frictional force microscopy has been shown to provide important structural information of the material and also to provide a material-specific contrast. And here I will show you how steel is a powerful tool to give structural information about organic semiconductors. So the first example I am giving to you here is for this organic semiconductor, PTCDI C8. This is an organic semiconductor used for N-type organic field effect transistors. And since the importance is the order and the crystalline quality of the layers on the dielectric, we study the nucleation and growth of the first layers on silicon dioxide. In this case here you can see a submonolayer coverage. So the molecules assemble forming these islands which have a height of 2 nanometers. This corresponds to this orientation of the molecules on the surface. So the unit cell in this molecule is very anisotropic because these molecules have a cofacial packing, and the shortest in plane vector is almost perpendicular to this scheme. And this is also the direction of the maximum overlap between the pi orbitals in adjacent molecules. Since the substrate is silicon dioxide, which is amorphous, you will expect a random azimuthal orientation of the domains on the surface. This is the frictional force microscopy image in the forward and in the backward direction. So you can see that there is a contrast between the molecular islands and the substrate. The islands appear with this darker contrast in the forward direction, meaning a lower friction of the tip scanning on top of the islands, reverse in the backward direction as expected. And let me here to introduce what is called the transverse shear microscopy. This is just scanning with an angle of 90 degrees. So in this case, we collect the torsion and the lateral force of the tip, while the fast scanning direction is parallel to the cantilever axis. And just measuring in this way, you can see that we can see this rich map of contrast. So you can see that some of the islands have one contrast, while some of the islands have two. And the sharp boundary between these domains already is giving us an indication that what we are visualizing here is the different crystalline the crystalline domains with a different orientation, with a different azimuthal orientation on the surface. In the standard frictional force microscopy, this is the lateral force image at molecular scale. We can see these molecular rows, which corresponds to this cofacial alignment of the molecules. And this is this stick-slip behavior I mentioned before at molecular level. Now, to demonstrate that this contrast is due to the different azimuthal orientation of these domains, let me show you the image in transverse shear microscopy at molecular level in this image. So here we focus on this region of the boundary where we can see the different orientation of the molecular rows, corresponding, as I was telling you before, to this pi-pi stacking direction. So this demonstrates that the signal of the transverse shear that we obtain in the torsion measuring by transverse shear microscopy is useful to map the orientation of the domains and is related with the orientation of the in-plane unit cell relative to the scanning direction. So this is very clear if I show you if I show you these molecular scale images measured at 90 degrees by transversal microscopy with these different 3 orientation domains. When the molecular rows are parallel to the cantilever axis, which is the scanning direction, you can see that the signal almost vanishes, while when we scan in this domain, the stick slip tooth shape is positive, related to the torsion of the cantilever when scanning in this direction, in this domain, while in this mirror-like domain, the stick slip signal is reverse and negative. So this shows that the sense of the torsion of the tip while scanning with the different orientation of the domains is what determines the contrast that we observe in the large-scale image. And a little bit more of this study with some theoretical modeling you can find in this publication. So the contrast that you will obtain in organic semiconductors will depend on the amplitude of the corrugation at molecular level, and this will depend on the molecular packing of the organic semiconductor. So this was for the first time reported from Pentacen, and in our group we have explored the contrast for different organic semiconductors. Now, for low cost manufacturing of organic semiconductors, one of the challenges is solution processing and to have large area coating of the films with uniformity and with large reproducibility. And this is a challenge because for those soluble molecules which can be processed in solution, the strong trend of crystallization of the molecules and the low viscosity of the solution somehow is giving a lot of the wetting problems and the formation of large crystals, which makes that the films are not continuous and not uniform. So in the last years, a surprising strategy was proposed to overcome these problems. And this strategy consists in mixing in the solution an organic semiconductor with an insulating polymer, most commonly polystyrene, to have the advantage of the properties of both materials. The semiconductor properties of the organic semiconductor to have high field effect mobility, and the ease of processability given by the polymer in the solution with the increased viscosity in the solution. And processing this blend in this way was giving, surprisingly, an overall rise of the charge carrier mobility, and I say surprisingly because this polymer is an insulator, and accompanied by a better reproducibility in the coating of large areas, but also accompanied by an increase of the air stability of the devices. So this strategy has been employed by for different combinations of organic semiconductors and polymers, and here I will focus on this particular combination. BTBT C8, which is one of the organic semiconductors with the highest reported field effect mobility in P-type transistors, is this molecule here with these two alkyl chains in combination with polystyrene. So what is the origin of all this improvement in the field effect mobility and in the reproducibility and stability of the devices? It has been proposed that the origin of the improvement is related with the stratification that arises spontaneously during the solvent evaporation, giving to the formation of a vertically segregated structure. And as you can see in this transmission electron microscopy image, here, it has been reported that the polystyrene goes to the bottom in the dielectric, whereas the BTBT-C8 crystallizes on top. And as I said, this vertical segregated structure has been determined and proposed for different materials combinations. So in our work, what I am presenting here, we use AFM to determine this vertically segregated structure with a nanometer scale precision and for different blend ratios. So this was a collaboration with our colleagues in the ICMAP, the group of Marta Mas. They were optimizing the performance of the organic field effect transistor for different blend ratios. And they found that for a BTBT polystyrene ratio of 4:1, the performance was the best, with an average apparent field effect mobility of 0.3, with high reproducibility of devices, whereas for the ratio of 1 to 2, I mean more polymer in this case, the reproducibility was very low, and also the current was much lower in the devices. So we also wanted to understand why. What was the impact of the blend ratio? So the morphology of the sample is not giving much information. You can see that the surfaces are very uniform with these micron-sized terraces here, with a height of 3 nanometers or multiples of it. And as you can see in this enlarged image, these are these terraces, which corresponds to the interlayer spacing of BTBT-C8, corresponding to this orientation of the surface. And this is in agreement with the well-known structure of BTBT-C8 on silicon dioxide. So now the lateral force measured in the standard frictional force microscopy is showing us two regions with two different friction, low and high. And if we zoom in the highest frictional region, we can see the molecular order that agree with this structure of BTBT, which corresponds to the herringbone packing of the molecules. And when we zoom on top of these low frictional areas, we can see not order, as expected due to the amorphous structure of the polystyrene. So with this, we can assign this frictional contrast with the two materials in the sample, polystyrene and crystalline BTBT-C8 with this orientation of the surface. So I will show you the analysis that we have been performed for this, in this case, this particular ratio, 1:2, and then I will show you the results for the three blend ratios. So when we focus on the polystyrene areas, and if we keep scanning and increasing slightly the force, because I have to mention that we get these images by scanning in contact mode with the lowest possible load, then we can see that the polystyrene can be removed. It has a height between 1 and 2 nanometers, leaving uncovered the BTBT-C8. And this we can check by imaging the molecular resolution on these areas, which now you can see the different friction. When we decrease the load, the polystyrene just covers again the surface. In this particular sample, we could find even a lower level. You can see here that it has a friction very similar to polystyrene. So it's attributed to a polystyrene-rich phase. And now, by increasing the load until reaching the substrate, we can measure the height also of this layer. And with this, we can obtain the phase separation of these two materials for this particular sample. So there is a bottom layer of polystyrene rich of about 3 nanometers, on top of which there is an incomplete layer of BTBT-C8, and on top of which there is this skin layer of polystyrene. So doing this kind of analysis for the three blend ratios, this is the result. So there is certainly a phase separation giving this tri-layer structure with polystyrene on the top with this very low thickness, which serves as encapsulation of the devices and to increase the stability, as I will show you in the following. With BTVT C8 in the middle, with high crystalline quality, which serve for the charge transport in the device, and on the bottom the polystyrene, which serve as the electric passivation of the silicon dioxide. So you can see that there are quantitative differences in the thickness of the BTVT-C8, being for the optimal ratio of the devices, the thickest with 2 complete layers and some islands on top. Whereas for the worst performing device, the 1 to 2, the first layer is not even incomplete. So in order to, before that, I will show you about the stability of the devices. So these are the freshly prepared devices with polystyrene and without polystyrene. And after several months, the BTVT C8 undergoes the wetting. This is a very well-known problem for this molecule, whereas the polystyrene stabilizes the morphology of the devices, and this is also reflected in the electrical characteristics with time. And now, in order to understand the impact of this phase-segregated structure for the different blend ratios at the nanoscale level, so we will performing Kelvin-proof force microscopy at certain locations in the channel of the devices during the operation of the transistors, just measuring the surface potential as a function of the gate voltage. For negative gate voltage, since this is a P-type transistor. So for the ratio of 1 to 2, in all the locations we examined, the surface potential follows a linear dependence with the gate voltage. This shows that at the nanoscale, the transistors are not working. There are no charges injected in the device to form the accumulation channel. So although the devices are macroscopically working, because there are percolation paths, at the nanoscale level, most of the area of the devices are not active. And this explains the lower current obtained in these devices. Whereas for the ratio of 4 to 1, the surface potential is not changing with the gate voltage because the charges are rapidly injected from the electrodes, forming the accumulation channel, and this screen the gate voltage. So the summary of this part is how the combination of frictional force microscopy and Kelvin-proof force microscopy is giving us nanoscale information about the structure, about the functionality, which explains the performance of the macroscopic devices. And now, coming to the last part of my talk, I was telling you that in many of the organic materials, like BTVT-C8, injection is a problem. Moreover, where the HOMO of the material is declined, like in this molecule. And one of the ways to improve the injection is to use a molecular dopant here on top of the organic semiconductor. So let me tell you a little bit more about molecular doping. So for P-type doping, we need a molecule with a high electron affinity, that is a low line LUMO respect to the vacuum level, so that electron charge transport is favored from the HOMO of the organic semiconductor to the LUMO of this acceptor molecule. Most commonly, the dopant is evaporated in the host material, but this, however, has adverse effect in the structural order of the organic semiconductor. Another way of doping is what is called surface charge transfer doping, where the molecular dopant is just deposited on top of the organic semiconductor. And this has been used to reduce the contact resistance in organic field effect transistors, but also to increase the surface conductivity of single crystals. For example, here you can see the increase of conductance when one monolayer of C60 is deposited on top of hydrogen-terminated diamond, just due to the charge transfer of the C60 with the diamond surface. So in spite of the importance of molecular doping, I have to say that the underlying mechanisms of molecular doping are not completely understood. So in our group now we are focusing on investigating this surface doping by exploring this molecular dopant, the fluorinated C60, on different organic semiconductors. Due to the fluorination of C60, this molecule becomes a very strong acceptor with a LUMO at about 5.5 electron volts from the vacuum level. It has a very high thermal stability, and due to this bulky shape, it has a very reported low interdiffusion in the dopant, even after thermal annealing. And in this first example, we will focus on pentacene as a benchmark organic semiconductor. Probably you know this is one of the best studied organic semiconductors with a relatively high charge transport mobility and with a HOMO that is about 4.9. So we expect charge transfer for this combination of materials. So since we are interested in the interface, we are working with a very thin thickness of pentacene of just few molecular layers, and the molecular dopant is evaporating on top. So first I go to the AFM level. Let me show you what in an in situ study by ultraviolet spectroscopy UPS study is telling us. By this method, the work function change, it can be quantified by measuring the secondary electron cutoff, and also the HOMO, the highest occupied molecular level of the pentacene, and how it changes when the dopant is deposited. So what we see by UPS is that the work function increases when the dopant is evaporated in 1 electron volt, and the HOMO of the pentacene is shifting about 0.4 electron volts towards the Fermi level, so giving us evidences of charge transfer. However, although UPS is a very powerful technique, so it's unreliable when you have an inhomogeneous surface, in particular in regard to the work function determination. So this is why we are using Kelvin-proof force microscopy to examine the work function at nanoscale level and to investigate the effect of the dopant in the first stages of the growth. So this is the topography of the pentacene for a coverage of 1.3 monolayers. This is the first layer completely covered, and these dendritic islands corresponds to the growth of the second layer. So the pentacene is standing upright in the so-called thin film structure with this upright orientation and forming the herringbone packing, very well known and reported. In the lateral force, by frictional force microscopy, is giving us these images. Probably the most important characteristic is these areas in the second layer islands, which indicates a low friction. Our hypothesis is that these areas corresponds to a higher crystalline packing of the pentacene, probably within plane register with the first layer of the pentacene. And this is the pentacene when we measure the lateral force in transverse shear microscopy. Here we can see the domain boundaries in between the different azimuthal orientation of the domains in the first layer. Now, when we deposit the fluorinated C60 on top of the pentacene, this is the morphology, the topography. The topography is showing us that there is one monolayer of C60 fluorinated covering the first layer. You can see in the friction, the change in the friction, whereas the nucleation and the growth of the second layer is not uniform. So it's covering this dendritic part of the islands, where the central part of the islands of the pentacell remains uncovered. And by X-ray diffraction, I don't show here, we know that the fluorinated C60 has a crystalline order on top of the pentacell. Now, this nanoscale morphology is also reflected in the surface potential as measured by the Kelvin-proof force microscopy. So you can see the surface, the lower surface potential in all those areas covered by the fluorinated C60 indicated a local increase on the work function of almost 1 electron volt respect to the uncovered pentacell. And exploring the earliest growth of the dopant on top of the pentacell. This is a pentacell island where you can see here is the first, second, third, and fourth layers of the pentacell. You can see that the coverage of the dopant depends on the layer number, decreasing with the layer number, and this is also reflected in the lower shift of the work function as a function of the layer number. So there is a correlation between the coverage of the dopant and the shift in the work function. So what we see is that there is a work function change, mostly due to the formation of an interface dipole by charge transfer. And now I will show you how this nanoscale morphology depends on the chemical properties of the organic semiconductor. So doing the similar experiment now with BTBT-C8, the molecule we saw before, in this case alkyl terminated. This is the topography, and this is the lateral force. So what we see is now that the fluorinated C60 is forming islands on the edges of the terraces of the organic semiconductor. You can see in the frictional force. And the dopant has a very highly crystalline structure, also proved by X-ray diffraction. And you can see the signature of this crystallinity in the polygonal shape of the islands. Now, this nanoscale morphology is reflected in the local work function. In this case, we were using a grid to pattern the surface, leaving some uncovered silicon. And this is the surface potential image. So this is the silicon and the silicon dioxide. This is the BTBT-C8, and this is those areas covered by the dopant. So with this, I want to finish. So what we show is that depending on the particular semiconductor, there is a nanoscale surface potential distribution, which is due to the nucleation or growth of the dopant on the surface, and this is in turn determined by the terminal group of the organic semiconductor. And of course, all these properties will be correlated in our group later with the contact resistance that we measure in the organic field effect transistors, but I will not talk about this here. So with this, I am coming now, this is another image in the nanoscale in this sample. So with this, I come to the end. So basically, the message is how the complementary information that we get by different methods, Kelvin-proof force microscopy and frictional force microscopy and shear transfer microscopy, allow us to combine structural information about molecular order, the size and orientation of crystalline domains, discriminate between materials with functionality like work function, formation of dipole, contact resistance, charge trapping, etc., and to understand the impact of these properties in the devices and to guide the optimization of the devices. So thank you very much. This is our group in Barcelona. These are our collaborators, and this is the funding. So thank you very much for your attention.